Hello students, these are your notes for Chapter 7, Section 5. This is Algebra 2. This is Mrs. Norris, and we are continuing to talk about logs. We're going to combine what we did in Section 4, so it's really important that you have those 5 different example types from Section 4 mastered. And we're actually starting with example 3 for this section. There are 4 different types of problems on here. Yes, A, B, C, and D. And they all look different, but their goals are the same. So if you can remember to tackle these problems by figuring out what's our goal is to get a single log. Okay, and once it is a single log, we're going to write them in exponential form, which none of you had trouble with when we started section 3. So let's start with example A here, 3A. This one's the easiest one because it's already a single log. It's the log base 6 of answer 2x minus 1 equals exponent of negative 1. And all you have to do when you have a single log is connect the 6 to the negative 1 like we do and rewrite it in exponent form. It looks like this. 6 to the negative 1 equals, continuing our circle, 2x minus 1. So we take away the log and we rewrite this whole expression in exponent form. Once we do that, it looks just like a pre-algebra problem. We can change this 6 to the negative 1 as 1 over 6. Okay, nothing happened on the right. Then we're going to multiply both sides by 6. That makes this a 1, and the right side becomes 6 times parenthesis 2x minus 1. Then we're going to distribute the 6 and solve for x, and I know I skipped a step in there, and the answer is x equals 7/12. So work that out yourself. You get 12x minus 6 equals 1. Subtracting and dividing, you get x equals 7/12. Alright, we're going to jump up here to example B, 3b. Is this expression a single log equals something? No. But we have a minus sign between these two logs, and the two logs have the same base. So the rule for minus, remember, this was example 2, is to take the 100 and the x plus 1 and divide them. When we have two logs being subtracted, and they're the same base, we divide the numbers that are behind the log. So we divide 100 by x plus 1. Well, we can't do anything with this yet because there's an x in it, but we do have a single log. Go back over to this example, just like we had a single log here. Log base answer equals exponent. Log base answer equals exponent. We're going to connect the 4 and the 1 and write 4 to the first equals, continuing our circle, 100 over x plus 1. This becomes another algebra 1 type problem. We're going to multiply both sides by x plus 1. Or you can think of this as cross multiplying. Multiplying by x plus 1 cancels this side, brings the x plus 1 to this side. We get 4x plus 4 equals 100, or x equals 24 when we solve that out. Okay, this is Algebra 1 stuff. I know I'm going through it quickly and skipping a couple steps to save time. Example C looks like it's almost a single log. We're almost to the point where we can just rewrite it in base form or exponent form. But this little 4 here is in the way. This exponent right here is in the way, so we're going to undo the exponent property or the power property from last night's lesson. And we're going to move the 4 to the front and rewrite it as 4 times log base 5 of answer x equals exponent of 8. Now again, we're very close to being ready to just write it in exponent form, but that 4 is in the way. So we're going to divide both sides by 4, and we get log base 5 of answer x equals exponent 2. And now it's really simple to put this in base exponent answer form. Base exponent answer. 5 to the second equals x, or x equals 5 squared, or 25. Jumping to example D, you should notice that again, just like in example B here, we did not have a single log, but we do have two logs being added this time with same bases. We divide when we subtract, but remember we multiply when the base is the same and we're adding two logs. So I can write this as a single log right away. Say log base 12 parentheses x, this guy, times x plus 1 equals whatever's on the right hand side, which is 1. Once we get it in this form where we have a single log, every time it's the same. The next step is the same. We make it 4 to the first equals the answer. We make it 12 to the first equals this answer. But when I multiply x times parentheses x plus 1, I get x squared plus x. Now that should look kind of weird to you at first. We're not going to be able to solve it, but we're going to use our rules from quadratics. We're going to subtract 12 from both sides, and now it looks like a simple factoring problem where we say what multiplies to give me negative 12 and adds to give me 1. Okay, now that we have our x squared and x and constant all on one side and we set it equal to 0, we can factor this, saying what multiplies to give us negative 12 and adds to give us 1. The answer is x plus 4 times x minus 3. When we solve this, we're going to get negative 4 or x equals 3. But what we have to realize is, there's a typo there, don't write that equals 0. But what we have to realize is you cannot ever take the log of a negative number. Okay? If you have your calculator handy, try it. It doesn't work. So our answer is actually just x equals 3. Okay, two more types of problems, and I know I'm going backwards here. This actually matches example 1 in the textbook. You'll notice that we have two problems given to us, and the x is in the exponent. In order to get to that x, we have to get rid of this base of 9 and this base of 27. So the goal here is to make sure you rewrite each side with the common base or the same base. And since 9 and 27, if you use your powers chart, both have a base of 3, so yes, they both have a base of 3. So all we did here is rewrite 9 as 3 squared, then copy that. Then rewrite 27 as 3 cubed, copy that. What happens next is just I to I multiply. We multiply the 2 and we distribute it into the 8 and the x, and we multiply the 3 into the x and the negative 3. So we get 3 to the 16 minus 2x equals 3 to the 3x minus 9. Okay, now that we have same bases, all right, that step was to raise a power to a power, multiply exponents. That's the I to I multiply. Now that we have same bases, what we can do is just pretty much write 16 minus 2x equals 3x minus 9. When the bases are the same, the exponents have to be equal. In order for that to be mathematically equal, then this expression has to equal this, right? For 3 to be 3. Or you could take the log of both sides, which does the inverse function. Now it's a simple algebra problem. Solving for x, we get x equals 5. All right, look at example B. So, just to refresh, you see these two powers, you see these two bases with exponents, x in the exponent, or the variable in the exponent. It's easy because we can rewrite them as same base problems and make their exponents be equal. However, example B does not have common bases. 5 and 4 have nothing in common in terms of basis that we can rewrite them as. When this happens, you can, just like you can take the square root of both sides, you can take a log of both sides. So we write the word log in front of each of them. When that happens, we're going to apply the power property of logs. We're going to take this x minus 1 and move it to the front. That looks like this. Then we're going to divide this log 4 by both sides. Looks like this. We get x minus 1 equals log 5 over log 4. This is a number that we can calculate on our calculator. We specifically left the base empty so we could use our calculator on this one. It means base 10. We're going to add 1 to both sides, and when you do 1 plus parentheses log 5 divided by log 4, you get approximately 2.61, 1.61. So that's the answer to x. What does that mean for our original problem? That means if I plug in 2.161 into this expression, I should get 5. So let's try it on our calculator. 4 caret 2.161 minus 1, enter, we get approximately 5. So we know that that was the correct answer. Alright, you have a couple of problems to try on your own, and I will see you tomorrow.